everyone, this is Dr. Walker. This is video 250, the guided examples for the motion of a charged particle in an external magnetic field. We're going to do one example in this video, and I already drew a little bit what was happening. We have an electron is accelerated through a potential difference of 1000 volts, and it then enters perpendicularly to a magnetic field. So basically, I drew the magnetic field going into the page and the electron entering going upward. And a magnetic field into the page would cause the electron to rotate in a circle like this. You can use your right hand rule number 1 to figure out that motion. But basically, it has to have some initial speed in order to start moving. And it's given that initial speed prior to entering that field. And the way that it's given that speed is it's accelerated through a potential difference. So if you remember, we've often drawn plates to visualize. If you have the plates here, and you visualize, say, the negative plates, the positive plates, and you know that if you have electrons that want to be accelerated here, then they're going to have a certain speed by the time they get to the positive plates, and it's with that speed that they're entering this external field. So this potential difference, delta V, is simply there to get the electrons up to speed before they enter the field. Okay, that said, we're looking for the radius of the circular orbit. We're looking for r here. So let's write down what we're given. I'd like you to try to write it down. So this is a guided example. Write down all the variables with all their values. Okay, let's take a look. We've got delta V is 1000 volts. And then we have the magnetic field B is 0.2 teslas. What else are we given? We're given more than that. So we know it's an electron, so we know the charge. And we only care about the magnitude of the charge. So we'll just do the magnitude of the charge, 1.6 times 10 to the negative 19 coulombs. The reason we only need the magnitude of the charge is because the equation that we just learned in the previous video, which was R equals mvq over b, it used the magnitude of the charge. Okay, so I already helped us out here by writing down the relevant equation that we're going to need to find the radius. So write down other givens. What about the mass? The mass of the electron. That is a constant that's given to you on your equation sheet, and it is 9.11 times 10 to the negative 31 kilograms. So at first glance, it seems, oh, this is just a plug and chug. I can just plug in all of these variables into this equation. However, the first variable that we have is the potential difference, but what we need is a speed. So you can see that this is going to be a two-step process. Before we can plug in the values, we need to find V. How do we find V? This goes back to a problem from the previous chapters where we can find V by looking at the potential difference that was accelerating our proton. Do you remember the equation that's going to give us the final speed? Assuming that it's starting from rest, how do we find a speed over here once the electron has gone through this potential difference? So the way that we were solving these problems is by looking at conservation of energy. And we have the equation that the change in potential energy, actually let me write this down here. Change in potential energy is equal to the negative change in kinetic energy. And the change in potential energy is Q delta V. So that means that the change in kinetic energy is going to equal negative Q delta V. And we know that change in kinetic energy is equal to final kinetic energy, 1/2 mv final squared minus 1/2 mv initial squared. So this is back from the old days. We learned how to do this type of equation, finding the change in kinetic energy and relating that to the final speed. So we're going to assume that it starts from rest here. so that way we can solve the problem. So V initial is 0, so this whole term here cancels out. V initial equals 0. So now what we need to do is plug in the values. We're going to solve for V final. So when you solve for V final, you are going to multiply by 2, divide by m, minus 2 over m q delta v. That's going to be v squared. Hopefully you can see that. Multiply by 2, divide by m. That's vf squared, and then I have to take the square root to get vf by itself. So now when I plug in the values, I get the square root of negative 2 over 9.11 times 10 to the negative 31. And then here we actually do need the negative q. The q is not an absolute value, so we do need the negative here for the q. And then the delta v was 1,000. So we plug all of those numbers in, the negatives will cancel out so that we can get an answer. And that's going to give us, and I'm going to kind of ran out of room here, I'm going to write it over here. Vf is equal to 1.87 times 10 to the 7 meters per second. Okay, so now that we have the speed, the V final here, which is the speed at which it enters the magnetic field, now we can plug in these values for this equation to get our radius. So our mass is 9.11 times 10 to the negative 31. Our V is 1.87 times 10 to the 7. Our charge, we just need the absolute value, 1.6 times 10 to the negative 19. And then our field is 0.2. So hopefully that didn't get too crowded over here. And that gives us a radius of 5.33 times 10 to the negative 4 meters. So that's our final answer. I like this problem because it does help us review a little bit of the past, and this is how you can accelerate electrons or any charges, right, is through this potential difference. They need to be moving before they can start moving in circular paths in these magnetic fields. Hope this was helpful. I'll see you in the next video.